draw these pictures as well. Got it? Okay. So this first picture is supposed to be kind of similar to what we drew yesterday. So it's a pipe of changing area. And so if the area is changing and the fluid is flowing, what else is different about, say, these two locations? Velocity? Yeah. Okay, because of continuity, right? As the area gets smaller, the velocity does what? Okay? So, what Bernoulli's does is kind of take that scenario, but look at more than just velocity. It really looks at everything, but in terms of energy. Okay? So if you remember back to last year, one of the most overarching laws that we had, especially second semester, was the law of conservation of energy. That says we can't what? That's right, create or destroy energy. So what Bernoulli's really did was take the law of conservation of energy and just apply it to fluids, moving fluids. And he got a law named after, or principle, or whatever you want to call it. Okay? So that's what this is going to be about. So if we take, say, this first region right here, just a dot that I labeled 1, right? Would it be moving? Would particles at this location be moving? So then what kind of energy would they have? Kinetic. So they're going to have kinetic because of the motion, right? Would there be gravitational potential energy at that location? Yes. Are you sure? Okay. What you have to know, what you don't know, is where is 0, right? What if 1 is where y equals 0? Then would you say there's any EG there? No. But if, say, y equals 0 is way down here, then could you say there's EG here? Yes. So because there could be EG here, we're going to go ahead and label it. But there are going to be some problems where you can neglect EG by just calling that location 0. Okay? All right. Would the same two quantities also be at location 2? Would they be equal in magnitude? No. No. But they would still exist, right? So you'd have an EK at position 2, and you'd have an EG at position 2. Okay? Last thing is the pressure. I want to be able to relate the pressure to this. So what I drew over here is a PV graph. And on this PV graph, just like any graph in physics, we can always analyze 3 different places: the intercept, the slope, and the area, right? All right? The shape of this doesn't really matter if we're just looking at the area, because the area would have the same units no matter what shape the graph was, right? And what would the units of that area be? So, yeah, pressure is measured in pascals, volume in. So what would be the slope of the area no matter what shape the graph was, or units? Yeah, units of the area would be a pascal times a meter cubed, right? But if you remember back to pressure, a pascal is really a what? A newton per what? Yeah. So what is that going to reduce to if I multiply by a meter cubed? Right. Okay. And if you remember back to AP1, there were actually two different quantities that had the units of Newton times a meter. Do you remember one of them? Not impulse. Work, not momentum. Hmm. Yeah, torque, right? So, what was the difference, do you remember, between work and torque? How did you know the difference? I mean, conceptually, they're very different. But how do you just know? Well, there was a condition for each. What was different about the work equation versus the torque equation? Kind of. What did you say? Linear motion versus angular motion? Not necessarily, because you can do work in angular motion too. It was perpendicular versus parallel. If you remember back to torque, the force that you used was 90 degrees to the radius that you used. So we call it a lever arm, right? They had to be 90 degrees to use the equation for torque. Work, it was the opposite. The two needed to be parallel. Okay? But more important than perpendicular parallel is just which one makes more sense here. So let me give you an example. Let's say you have a balloon full of air. Okay? And you have to remember, air is different from a liquid in that it's what? Good. So if I could take that balloon and squeeze it, what would I do to its volume? And therefore, what would happen to its pressure? Increase. Yeah. So decrease volume, increase pressure. For that situation, it'd be inverse, right? But again, the shape doesn't matter. But the bigger aspect is, do you think torque is occurring, or do you think work is occurring? Work. Yeah, because remember, in conceptual nature, work is just the transfer of energy, one of the three ways to transfer energy. Do you remember the other two? Radiation and heat. Okay, two that we're going to learn this year in AP2. All we did really out of those three was work last year. Okay, so when you squeeze a balloon, you're doing work on the balloon. You're transferring energy to the balloon, right? So this unit here makes much more sense representing work than it does torque. So that's what it is. The area of that graph is what we call work. Okay? So, since work is a change in energy, and then these are quantities of energies as well, then all Bernoulli did is take those ideas and apply it to conservation. So he said the total energy here has to be what to the total energy here? Equal. Yeah, so all I'm going to do is write that out as an equation, okay? So if we start with, let's say I want pressure in the equation. Well, to relate pressure to kinetic and gravitational energy, I want to multiply it by volume. So PV gets me a quantity in joules. I can add that to kinetic energy. Does anyone remember the equation for kinetic energy? mv squared, and this is a different v, so you got volume and you got velocity in the same equation. Okay, be careful. So I'm going to say that's v1, the velocity at this first location. And then do you remember the equation for Eg? Okay. And I'm just going to use y here instead of h, because again, h gets a little tricky. We use that for depth. All right. So that's the total energy at position 1, and all conservation says it has to equal the total energy at position 2. So you write the same thing, but for position 2 over here. Okay? There's one more change we're going to make. It's very common in fluids not to work with mass, but instead to work with density and volume, right? So I could actually replace mass in these equations with what? not over. Yeah, this would be density times volume. So if I take out every mass and replace it with density times volume, then all of a sudden I see volume in every single quantity, which means I can do what to it? Yeah, so I'm going to get rid of volume in every quantity. And then that lets me write what is often the final form of Bernoulli's principle, or his equation. So 1/2 d squared g. It is the longest equation you get in either AP1 or AP2. Okay. Yep.
And when you put in the D, you mean density.
That's right. D here is density. So on your AP formula chart, remember they don't use D, they use the rho. You'll see rho where these D's are.
Is this on?
Mm-hmm. It's on the formula chart just like this, except again with rows instead of D's. Okay? Now, the reason I took you through the derivation is because when you do Bernoulli's mathematically, it's not too bad. You just plug in numbers and solve for your unknown, that kind of thing. But when you do it conceptually, it's very helpful to understand something about this equation. That this right here is basically related to the work done on the fluid in that section, right? This right here is basically related to the what of the fluid? Kinetic energy. And then this right here is basically related to the what? Yeah, it doesn't directly solve for it, because remember we got rid of something. But it does create a number that's related to it. Okay? So to kind of show you how that works conceptually, let me give you another example that we can analyze. So let's say I have a pipe that elevates. Okay? Alright, let's say this pipe has a constant area, and then I'm going to analyze two locations in this pipe, which can always be random. There's no reason one has to be before two. It can be any two locations, in whatever order you want to make. Okay? So, if I have this situation, let's start with what's the easiest to analyze. Let's start with the EG. What's going to be true about the EG at position 1 compared to the EG at position 2? Which one's less? Yeah, that should be pretty obvious, right? Because 2 is higher, it's going to have more EG. Everyone gets that, right? Pretty simple. Okay, now a little bit harder question is what about the EK at the 2 positions? How do you think that might compare?
This will be greater than 1 because equal. The same or has the same.
Why?
Area. Because pressure is going to be greater than 1.
Well, the reasoning is really this. Okay, and we'll get to pressure in a second. Okay. So the area stays constant. In continuity, which can't be broken, okay, says that if the area is constant, the velocity is constant. If the velocity is constant, the kinetic energy is constant. So kinetic energy is not changing. So what's really tricky about Bernoulli's is that there's 3 quantities to worry about. With continuity, there was just area and velocity, right? You change one, you change the other. Here there's 3, and you always, in any problem, have to analyze all 3, okay, to get it correct. You can't just take 2 of them. So now that we've analyzed those 2, let's look at pressure. How does the pressure have to compare using Bernoulli's to justify it? Yeah. So if EK is equal, then this 1/2 dV squared just kind of factors out of the problem, right? It's the same on both sides. Then you look at this quantity, which is related to EG. If this one's bigger, then the pressure on that side has to be smaller. Yeah. So if EG2 is bigger, then pressure 2 is smaller. Okay? That makes sense? Now be careful. If you're sitting there thinking, well, this was obvious because this one's deeper, remember, pressure due to depth is a static concept, not a dynamic concept. It is possible to have this flip. And that's one I want you to now think about. What could I do to this situation to create a place where P1 had less pressure than P2?
Change the area.
How would I change the area?
That's an egg.
Make the area larger.
Area larger where?
Around 1.
Okay, if the area gets bigger here, what happens to the velocity? So it would have less EK and less EG. So it would need even more pressure, right? So we wanted to do the opposite. Instead of making the area down here bigger, we want to make the area down here much smaller, because that would then create more velocity. More velocity means more EK, and if I get this increased to a rate that's larger than how low it is in terms of EG, then more EK could lead to less pressure. Does that make sense? So be careful memorizing scenarios, because there's 3 things to factor in. And in any scenario, I can tweak one of them, and that can have an effect on the other 2. Make sense? Okay, so your last worksheet, worksheet 8, is going to take you through some scenarios of this. And I would say, actually, I've seen more conceptual questions over Bernoulli's than math questions. But you will have a mixture of both. And this is on your formula chart. You just need to kind of understand it. All right? Does that make sense? The other demo of Bernoulli's I can do to show you, this is very common. You may have seen this before in another class. But this is also pretty profound, because it pretty much gets to why airplanes fly. Okay? But if you take a piece of paper and you kind of hold it like this in front of you, and then you blow over the top of it, right? What does it do? Yeah. Did it accelerate? If it accelerated, that's because there's a net force. How did I create a net force? How did that create a net force? I did not create more pressure at the top. Okay, be more specific though. What is it? Yeah, so by blowing across the top, I gave the air on the top more velocity. More velocity means more kinetic energy, right? Did I change the gravitational energy of the paper very much?
No.
No, I mean just a tiny bit, but pretty negligible compared to the ground, right? I'm holding this part still. So EG you can kind of factor out of that scenario. So it's basically, if the velocity becomes greater, the EK becomes greater, what does that do to the pressure?
Pressure on the bottom increases.
I didn't really do anything to the bottom. But what happens to the pressure at the top? It's now lower. So we have the original pressure, which is air pressure, 1 atmosphere at the bottom, but I now have less pressure on the top. Okay? There's very few always in physics, but in fluids, there's 2 key ones that relate to Bernoulli's. One, energy is always conserved. That's basically what Bernoulli's is saying, right? But the second always is that fluids will always flow from high to low pressure, right? So if I create low pressure on the top, and there's the original pressure on the bottom, then I'm going to create what kind of force? A buoyant force. And it's that buoyant force that provides the net force that causes it to accelerate upwards, right? That's how I can achieve lift. So how does an airplane achieve lift? They create lower pressure on top of the wings. Okay? How do they do that? Do what? Yeah. by actually airplanes, they create what's called thrust. Okay, they have to be able to move forward to get the air to go over the wings. Okay, but it gets a little tricky. Just because the air is going over the wings, why does that cause lower pressure on top, higher pressure on the bottom? It is how a spoiler works. But how does it work? Isn't air moving across both the top and the bottom of the airplane wing? So then, if air is moving on both sides, it must be moving faster. That is undeniable. Okay? Everyone in aviation agrees with that fact. But why is it moving faster on the top? Do what?
Doesn't the airplane have to get a slight downward angle?
Yeah. Why does that matter? So aerodynamics gets a little tricky, okay? And believe it or not, physicists don't 100% completely even understand why an airplane flies. Makes you feel great next time you get in an airplane, right? It's a whole lot of trial and error, okay? It's a lot of engineering. We don't understand everything, but we have a much better idea. To be honest with you, what I was taught when I was like your age, or maybe younger, I think the first time I heard this was maybe like junior high. Okay, have you heard of Bernoulli's before? Did you hear about it before today? Never? Sometimes I teach in junior high. Anyway, but what I heard in school is just wrong. Okay? and the details of it are much more complicated, so I understand why the teacher didn't get into it, or maybe they didn't know it. But what often gets explained, if you see anybody ever explain it like this, is that the top of the wing is curved, the bottom is flat. Okay? And so what I was told in school is that the air molecules on the bottom don't have to go as far. The air molecules on top have to travel a further path. And since they travel a further path, they must go faster. Because they're going faster, it's lower pressure and the airplane goes up. Let's go on to the next topic and not ask any questions, okay? All right? So, yeah, but what never made sense is why. Why is it having to go faster because it's going further? Like, that didn't make any sense. So, the truth is, what gets created above an airplane wing is actually called a vortex, and it's like a tornado. And it's not really facing us, it would actually be facing like the front of the airplane. But you get these vortexes on top of the airplane, like spinning tornadoes. And if you remember what we talked about before, storms like tornadoes and hurricanes, those are just areas of low pressure, right? And so you're creating low pressure up here with the vortices, and you have the original pressure down here, and you create lift. And then that's the other thing that's true, is there is an aspect where the wing is kind of curved, like when you're trying to lift off, they go up a little bit. So the wind on the bottom also hits and just does a momentum conservation type of thing, and it can actually force you to lift up. So it's really a multitude of things that causes lift. And this is just the simplification of it. But the good news is we don't deal with gas fluids because of the compressibility issue. So we don't get into that part of it all. But the fact that you do create low pressure on top of the wing and high pressure on the bottom is absolutely solid, and one you can go with to try to explain why an airplane takes off. Okay? Yeah?
Landing and they like open up the flaps, is that to like do the opposite of like so it'll help slow down the plane?
Yeah.
So like stop there.
Mm-hmm. Mm-hmm. Yeah, because it's a balance between so many different things when you're flying. Because the more that you angle the airplane, the more of that drag you're going to get, which will slow you down in one axis, even though it's providing you a force in a different axis. So it's a trade-off, and that's why when a plane does that, if they go too slow, they can stall, and their engine stops for a second, and they have to, try to start it back up. So there is definitely a skill to being a pilot. You can't just jump in a plane and expect to be able to do it. Okay. All right. So that's Bernoulli's, and we have one more thing to write down related to this. Torricelli's special case of Bernoulli's. So, yes, more Italian. All right, now, special cases are often or sometimes referred to as shortcuts in physics. And personally, I'm not a fan of shortcuts. Okay. Again, throughout AP1, you might have seen different things, especially if you're in KVA trying to navigate it all on your own a little bit. But special cases are kind of shortcut equations you can use in physics. The problem with shortcut equations is that they have specific conditions. And if you meet those conditions, you can use the shortcut equations. But if you don't, you can't. That's why I don't like them, because what you're doing every time you memorize a shortcut equation is you're having to also memorize the conditions that go with it. And I'm a big fan of not memorizing, or memorizing as little as possible. Okay? Because memorization requires repetition. You have to use it all the time. If you're not using it all the time, you're going to forget it. Like foreign language. Okay? Something like that. All right? With that said, this is one of the few shortcut equations we do talk about, because I have seen it on the AP exam. Okay? So we're going to go ahead and mention it. So Torricelli's really boils down to one scenario. Is when you have something draining to where the area of the top opening is drastically bigger than the area of the bottom. So that's the condition that has to be met. That this A1 up top has to be much bigger than A2. And there's not like a cutoff. It's just the bigger the difference, the more accurate this becomes. The smaller the difference between those, the less accurate it becomes. Okay? So if A1 is drastically bigger than A2, imagine like a 2-liter bottle of fluid, right? And you take just a little pin and you poke just a tiny little hole at the bottom. Is it going to drain really quick? No. It's going to take a while for this to drain out, right? And so the bigger the difference, the more we can approximate this velocity up here to be 0. And why that applies to Bernoulli's is because if we have a 0 velocity, we can say there's what kind of kinetic energy? Yeah. So if there's no kinetic energy up here, all right, the second thing to look at is pressure. Both of these, because you poked holes, are subject to the atmosphere. But the atmospheric pressure up here and the atmospheric pressure down here are going to be the same. So then that also cancels out, right? So if you don't worry about pressure, and kinetic energy at the top is 0, then all there is at the top is what kind of energy? Gravitational. That gravitational is going to basically turn into what down here if we call this y equals 0? Kinetic. So you basically just take the gravitational at the top and set it equal to the kinetic at the bottom, simplify it, and you get this equation. But more important than the equation is what it's saying. So I've seen Torricelli's asked about, but I've only really seen it asked about conceptually. Although, I mean, maybe I could change that in the future. Never see AP exams till after they give them. But what this is basically saying, okay, G is gravity, right? The gravitational field strength of 9.8. That's not going to change unless we go somewhere else, right? So what it's basically saying is how fast this comes out is only dependent upon a single thing. And what is that single thing? Yeah, the depth, right? How deep it is. Okay, and again, this should kind of make sense. If you did have a container of water and you poked a hole, what would happen to this stream as it started to empty? Would it always go out the same distance?
No.
Okay, would it start to go further or start to go less far? Yeah. And why is that? Okay, because the depth gets smaller, it has a lower velocity, right? Does that make sense? Okay, now you say it makes sense, but then I can ask you questions to ask you, what happens to the velocity of this stream if I make A2 a little bigger?
Yeah, it's running the special case, but it'd be less accurate if it's
It would start to be less accurate, yeah. But still, what would happen to it? According to Torricelli's, nothing. But what happens here is sometimes you get velocity confused with flow rate. Okay? Flow rate is how much volume is moving per second, right? Not necessarily how fast the molecules are moving. So this is talking about how fast the particles are coming out. Okay, if I increase the area, would the flow rate change?
Yeah.
Absolutely. But would the volume change? No. I mean, not the volume, sorry, velocity. The velocity wouldn't change, right? So the flow rate changes, but the velocity doesn't. What if I make this container wider, but not any deeper?
Still the same, so the velocity.
Still the same velocity, right? What if I made it taller and deeper? Then it'd go out faster, right? Okay? So there's lots of different changes you can make. What you have to remember, or what you need to remember, is that the speed that this comes out at is really only dependent upon the height. Okay? Yeah.
So if the two areas are the same, then like the way it wouldn't work.
Yeah. It would drain way too fast. Okay? So Torricelli's is a special case. Now, the other question is, what do you do if it doesn't fit Torricelli's? Then you just go back to Bernoulli's. Okay? So this is still Bernoulli's. It's just a special case of Bernoulli's. Okay? So that's all. It's just a special case of Bernoulli's. If you forget about Torricelli's or don't need it, then you can always go back to Bernoulli's. It's just this is much faster. And if you remember, speed on an AP physics exam or a test in class always matters. Tests are long, right? So you can get by without remembering Torricelli's, but it's going to probably cost you time. Okay, because you go through the whole Bernoulli's. Right? All right, so keep that in mind as you start studying for the test, which is when? Yeah, Wednesday. So we have tomorrow, and then we have Tuesday, because Monday's a holiday. And then we'll have our first test. Okay? All right, let's start checking worksheet 7. We're not going to finish it, but we'll start checking some of it. So get out worksheet 7 and a red pen.